start streaming and recording. So we can save it. Now the question is, how many bees will be, what's the probability that all bees will be pollinated? Now along this branch here, it's clear that that probability must be 0, because we've already made 1, 2, makes 4 moves, okay. Then we would have to continue that. And there's still a chance, so we would have to, each one of those will have its own tree, a copy of this particular tree here attached at each level. It's 2 more moves that the bee makes. It say it flies 3 more times or 4 more times? Oh, 3 further random flights, sorry. So it says 3 further random flights, and probability that all flowers will be pollinated, cross-pollinated. So we've already done 2 flights, and then here we have the probability that we get to this state, which is 1/9. Now we have to set the probability that we will get all flowers cross-pollinated. Now in this case, this is with probability 1. The probability that we will cross-pollinate all flowers is 0. Because we go flower 1, flower 1, flower 1, so we wasted 2 flights staying at the same flower. Now I can go to flower 1, 2, or 3, doesn't matter, but I'll never be able to cover with 1 move flowers 2 and 3. So that will have a probability of 0. Then let's have a look at what happens in this case. Let's have a look what else I have. Flower 1. If I go flower 1, flower 2, flower 3, then it's also clear that we will have a probability of 1 that we pollinate all the flowers. Why? Because we already go flower 1 to flower 2 to flower 3. So we already visited all of them. So that means guaranteed we will have cross-pollinated all of them. The same thing is true for this branch. Because I can go to flower 3 and then flower 2, then I end up also having pollinated all of them. So now we have to look at the other possibilities. And let's have a look at this branch, for example. So here I have two choices now. I have flower 1 and flower 2 pollinated. And with 1/3 probability, I will fly to flower 3, right? Oops. And then I have all pollinated. Or I fly to flower 1 or 2, doesn't really matter which one, in which case not all of them will be pollinated. So this will be, it's pretty cool, you can put the this is 2/3. Let me see. Let me actually do this. This is pretty neat. I didn't know you can put edge labels like between the connectors in Draw. Hey. So, oh, it split them. So here the situation is the same. 1/3 we will fly to flower 1, flower 2, sorry. 1 or 3 will visit with 2/3 probability. If we go to flower 2, we will pollinate all of them. Every other case, we won't pollinate all of them. Similarly, now this will be copied to all of them. Oops. And then let's see what the answer is. So probability that we reach a 1 here is 1/3 times 1/3 times 1/3. So that's 1/27 plus, here it's the same, 1/3, 1/3, 1/3. So there's another 1/27 plus another one here. And now I counted 1, 2, 3, 4. Yeah. 1, 2, 3. Now another one. Then the next one here is 1/9 to get a 1. Or 3/27 plus 1/27 plus 7 plus another 3/27 plus another 1/27. So there's 2 that have a probability of 3/27, those 2 branches, this one and this one, those 2 paths, and we have 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, 1/27, so that should be 12/27 if I want to answer the question. Then let me save that. Then I can open this up in an Explorer, copy it to here. to present it as a byte array. And here's our graphic that we just made. And here's our solution. I guess I should have put that here somewhere and put it in a box. Oh, this is a square. Don't want that. Here's a rectangle. And then I'll update that later on to the back. So now let's see what the BBC said for the solution. 4 over 27. How come? So on. Then there are only 4 journeys possible which result in all flowers. And that's true. So how come my reasoning was wrong there? 1, 2, 1, 3. Landing on any flower. Let me move that out a little bit. So first flower, so we have 1, 1, 1. Flower 1, flower 2, flower 3. One over 9. Then they're all pollinated, and 3, 1. So here we should have 1, 2, 3, 1 and 1, 2, 3, 2. Why don't they count 1, 2, 3, 2? So that's I don't understand this answer, because it says the bee flies 4 times, so it can go 1, 2, 3, 1, or 1, 2, 3, 2, or 1, 2, 3, 3. So all of these would result in all of them being pollinated, but they only counted as 1 out of the 27 options. So I think our interpretation of where the moth goes after it pollinates all of them is slightly different. because yeah, if the, and here that should be 1 1 2 1 3 or 1 2 2 3 should also lead to all of them pollinated, not just 1 2 1 3. Being pollinated. 1 2 1 3. So I'm not sure why that comes up with this solution, but more importantly, now we're doing robotics, we're doing computer science, so 4 out of 27. Said out of 27. 1/3, 1/9, 1/27, and then they all follow. Yeah. So let us generalize the problem. And then use a computer simulation to find the answer. So the first generalization is to vary the number of other flowers and the number of bees that are entering the yard. So let's say that there are n flowers, or let's make that one a proper variable. And moths that are entering the yard, the garden, and assume that each moth flies and moves in the garden. And we define cross-pollinated as has been visited by bees that came from different flowers. And then let's see when we plot that if we see anything interesting. So now I give you 15 minutes as an exercise, as a quiz. You can implement the simulation as defined in this slide and the BBC puzzle. Right? So good luck. Think about how you would structure your program in order to calculate the probability that all the flowers in the garden will have been cross-pollinated. Or another way of asking that question is, how many bees does it take to have a 90% chance that all flowers will have been cross-pollinated, assuming that each moth will fly will make n moves in the garden. I think I set up the wrong. Oh. So we import some libraries, NumPy, random, and math, and now we have to set up the number of flowers. The information that I need to track for each flower is whether it has been cross-pollinated or not, right? So that could be represented by just a Boolean, but I'll just use integers. So the flowers are going to be all initialized to zeros, and I need n flowers of those. So here's our thing, and there were 3 flowers and 1 moth, and it flew 4 times. So right now I haven't done anything, I just get the 3 flowers. So now I need to set starting points for the moth. So the moths are all going to start at some flower. So I need to generate random start flower positions for them. The low value would be 0. The high value would be the length of the number of flowers that we have, or n flowers. And the number of moths and they all start at some random flower. And moth and month. Now in this case, I call it with just one moth, so it will be a it will be the only the one moth position. So in this case, it would start at flower number 1. But I have the labels the flowers labeled 0, 1, and 2 rather than 1, 2, 3. Just like we count things in computer science, always with a start index of 0. So now I have the flowers and the moth. Now I need to make the number of moves. So if it's 1, then it will go 1 time, yes. And then I need to move the flowers around. And I need to keep track of which pollen the moth have visited. So I need some more information about the moth. So I will set up another array of the history, the path that the moth has been taken. That would be F for F in moth. And that would be a list. So we just want to make sure that our data structures are sort of looking correct. Now I know where each moth came from. Now I can move them around. So each moth is going to go to a different destination now. That is going to be independent. So any moth can go to any flower at any time. So this is where the moths are going to move. And now I need to check if the flower has been pollinated. So cross-pollinated, I think, in this context means that there have been bees that have previously been at two other flowers, or one bee that comes from one flower and one moth that comes from one flower and one moth that comes from a different flower. So that actually means that the flowers here, this is not really a good data structure, because I need to remember what bees, with which pollen they were loaded. What bees have visited that particular flower before. So that would be an empty list. Nobody has visited the flowers. Actually, yeah, because at that point the moths are all, they come into the garden without any pollen. Then we have a destination. So now for D in destination, that now means that and I need the index. Now moth number I will fly to flower number dest I. So the destination is, oops, I thought I am, okay. Okay, somehow it got turned off. Sorry about this. I will share the screen, yes. Not this one, sorry. So can you see it now? Okay, good. Yeah, sorry about that. Please let me know right away if there's any problems with the streaming. Also, as I said, you can watch it on twitch.com, which is independent of the Discord. So here, update information. No. Twitch.tv.
About it. That's all you're gonna get.
Yeah, okay, So that's it.
Yeah.
Share.
Okay. So that's it. Yeah.
Copy
Share.
URL.
So that's it. Yeah. Copy
So this is another way to watch it.
So this
But
is
it
another
has a
way.
little delay. Okay, good. So now we're talking about this code here to actually implement the cross pollinate function. Let me be consistent here with my naming style, even though in Python the split case is more common. So that's a destination flower that we want to go to. So now for flower 4, flowers d dot append dot extend, and I need to add to the current history extend this is where the moths are, so that should be flowers, yes. And history I. And then I need to update the history for each one of the moths to see which other flowers they have visited. And so that would be history, and each one needs to be appended. So that will be history I dot append destination of moth I for I in range for M actually I just write it like this, for M in range and moth history M dot append destination N. So let's have a look and see what happens. If I run this code, then we have no flowers, moth starts in 0, history in 0, and then end object range and moves. So first, all the flowers have not been visited by any moth. Then the moth starts in with flower 2. So then it moves to flower 1. So now flower 1 will have been cross-pollinated from flower 2, and then it moves to flower 1. So now the moth is goes back to flower 1. So now this flower here has flower 3 has the pollen, or has been cross-pollinated with 2 and 1. And so the moth went 2, 1, and 2. 2, 1, and 2. And it said 4 moves. 1, 2, 3, 4, 5. So 4 flights. Print 1 extra 1 here. So here's another run, and we start out with flower 2, then we go to 2 again, and then we go to 1, and then we go to flower 0. Okay, and I just realized why my answer here was incorrect on that chart, because yeah, that makes sense now. The flower, if I go from 1 to 2 and then 3, then I have pollen matter from 1, which will be shared with 2, and 2 and 3 on 3. But I think they want all flowers cross-pollinated. Right now, 1 has not been visited by anybody. So it's not enough for the moth to travel from 1, 2, and 3, but it also has to go back to 1. And that's why the only options are 1, 2, 3, 1, and 1, 3, 2, 1, and those versions. So this answer here is incorrect given the assumptions that the BBC made. Yes, right now, if I go 1, 2, and 3, then here I have to go back to 1. So otherwise, only the bee will have only visited 1 with no other pollen. So now we can solve this here correctly, and then this will actually should work out to be the same answer as the BBC puzzle gods figured out. Now I want to, after I made all my moves, I want to check which, for it to be cross-pollinated, that means that it has more than 2 unique entries in its visiting history from the different flowers. So here's the moth, this is extend, so this should be correct. This may grow a little bit too big. In theory, I should be able to make this a set. Because I don't care if 2 bees with material from flower X have arrived at flower Y. So the check then here is for each flower each one of the flowers, I must have at least 2 unique elements in it that are not the same as the flower name. So how can we check for that? One way to do it would be to generate a dictionary. Actually, now we use a set. Okay, let's use a set from the beginning then. And the problem is now set is no extend, it's flowers d and history I. And I think that needs to be star star there to convert it into a list. And let's say that to make the code easier, we can also say that each flower was visited by itself. Now if the length of f is less than 3, if it's 1, if it's 2, if it's 3. If it's less than 3, then not a mapping, so let's take these lists, Python set append, okay. So that means we need to add an element. The element that we need to add is all the elements for the moss. Let's try that. Okay. The flowers. So now after this run, for example, we have one flower, flower 0, that only received material from flower 2, flower 1 which received material from 0 and 2, and flower 2 which was only visited by no other bee with material, so it only has material from 2. And for this particular run, I can then check if they were all pollinated. So here it says false because, yes, no, they're all false in this case, and then we can run it some more times. Zero, 1, 2. The history went 1, 1, 1, 1, 1. So it started at 1, then it went to 1 a whole bunch more times, and then 1s to 0. So here this one has material from 0 and 1. So now I can run this as a simulation. Run it 100 times. So this is the version in the puzzle, I think, 314. So 4 moves, 1 moth, 3 flowers. This is how many we try out. So if all pollinated, we add 1 to the success. much printing. So it says success rate 0.06, and here we can see the flowers moving around and the moss moving around the flowers. So let's pick one here. Started at 2, then went to 0. So now flower 0 has a material from 2. These ones are a limit. Then goes back to 2. So now these ones have material from 0 and 2. This one has materials from 0 and 2. And then if it were just to go to 1, then but now the trial is finished. So right now this was that. Let me open a calculator. Four over 27. 0.14. So my success rate now, if I count it like that, is less than what we would expect from the BBC solution. Uh, 0.06 in this scenario. So let's run a couple of more experiments. Let's run 500. No, and I get rid of all the print statements so that we don't move so much. Zero point 0.058. So let's stick with this interpretation now. Let's have a look and see what happens if I make the bee fly around for longer. So instead of making 4 moves, let's say I make 8 moves. Then the success rate is over 50%. Right, 0.52 now. So let's plot this data to see what happens with the success rate. I define a new function to run a trial, the number of tries, and here we can actually do some pretty neat thing. We can use currying create a trial. Now for the trial I need to know the number of flowers number of moths, and the number of moves. And then since closures and functions are first-class citizens in Python, I can actually create a new function here. I can write a function, create trial, which will return a function. The function that it returns is a function that has no arguments, but internally here, because technically what this is called a closure. In this case, I can use variables that are outside of the scope of that function at this moment. So here I define a new function which basically takes these arguments for flowers, moths, and moves, and it generates a new function that and I think that's the correct syntax. Generates a new function which now has 0 parameters, so I don't need to specify anything. So I can now write a function which will run these number of trials without having to specify the parameters here always. So I can just say that this is calling the function. Then it returns, and I return the percentage of fully pollinated garden. So R is equal to run trial for 100. Let's run 10 only. And the function is create a trial for, what did I have? 3 flowers, 1 moth, 4 steps. So here's our success rate. That syntax is wrong. How did we do that? Okay, no. success rate 0. Oop. So let's try 100. 0.05. Yeah. So now, since I need to move to all the flowers, that means the minimum number that I need in order to be able to pollinate, cross-pollinate all of them is the number of flowers plus 1. So let's vary this one first and see what happens. So I want to try and plot it. So let's say from 0 to 50 moves, number of steps 25. Run the trial, number of trial size, let's run it just for 200, 100. And the function would be create the trial, and that would be 3 flowers, 1 moth, and X M for the number of moths being in X. And now we'll demonstrate some of the nice features of Matplotlib. So now what I have is a data set and I can set the title, cross pollination success rate, I can set a label, that's the number of moves for each moth. X label is the success rate. And then let's plot it. So for plot, the first two, the most important arguments is the x coordinates of the points that I want to plot as a line. So in this case, that will be x, and the y coordinates. They must be arrays usually. Y could be a n+1 dimensional array. Then I can specify that I want to connect them with a line, and I say that the color of the line is red and the line width of the color is 3, of the data is 3, and then now I could just call plt.show in order to show it. So if you write this on your own computer, then you can just call plt.show. I have to use slightly more complicated version because I want to have them in the slides. Oops. Since I use them as an argument for range, that means it must be an integer. So I make sure I force it to an integer. And here we can see our cross-pollination success rate. As you would expect, eventually, of course, the probability sort of is at 1, so it can't grow any further. It will saturate eventually. So if the moth makes more than 20 moves, then the probability that it isn't able to pollinate all the flowers, all the 3 flowers, is extremely slim. Of course, until we make at least 3 moves, the probability, at least 4 moves, the probability of cross-pollinating all flowers is going to be 0, because we won't be able to reach all the flowers in 3 moves, for example. We need 4 at least to get to all of them. And this is sort of the interesting part. You can see the probability of pollinating them actually grows very quickly. So then let's make that a little bit more interesting. Let's start with more flowers. Let's say we start with say a quarter, 50, so 10 flowers, and then number of moves, number of moth, so let's check the number of moths. Simply keep incrementing them, starting with 1 moth up to also quarter, sure, 10 moths, and increment them by 2. call this the y's now because there's more than one. For each one of those, plot it. I let the matplotlib select the color and I change the line width to 3. And M moves. And here we can see our chart now for the different number of moth. Let's increase the number of flowers. So let's say 20 instead of 10. And I want to set a label. So use the Y index. So number of moths should be 1 plus 2, 1 plus 2 times yi. Plot the legend. And so here we see, so with 20 flowers, the number of moth, if there are 1, then up to 50, only a very small probability that all of them will be pollinated. If we have 3 moth, then that grows here, 5 moth, 7 moth, and 9 moth. So now I could run this with more trials. I could record the variance of the data as well. That will be important to see how much these results change, but for a little preliminary investigation, this is sort of kind of interesting. Right? I'm still not sure why my simulation now gives us a different result. The BBC comes up with 0.148, 4 out of 27. In my version, I end up with 0.05, so it seems to be harder to satisfy my criteria. But I'm not sure exactly what the difference interpretation could have been. It seems that looks okay. Now, since I'm Since I'm not an expert on moth and pollination, I'm not sure how this actually works. If they need to be flower 1, so 1, 2, 1, 3, 1, 2, 3, 1, 1, 3, 1, 2. 4 times 1/3 to the power of 3, or multiplied by 3. Yeah, so 4 times 1/3 times 3 should be 4. 1/3 to the power of 3. 1/3 times 1/3 times 1, so it must be to the power of 3, so that would be 4 over 1 to over 27. So if we call the first one 1, then it would go to 2 or 3, then it can go back to 1, then to the other one over. So this seems correct. Not sure why I wouldn't count that. So if we go 1, 3, 1, 2, let me, in order to debug this, let's copy this slide, because it's the one where we actually run our simulation, and let us here's the problem. Should break here. That wouldn't actually change the result, though. That would only yep. Three, 1, 4, yep, correct. So I want to print out if all pollinated, then print this information to see what solutions we actually get here. Zero 1 2 0 1 2 0 1 2. The history of the moth. 1 0 2 1 0 4. One 2 0 1 2. So one thing is that I don't count the initial let's just run one trial. So moss goes from 0 to 2, 0 to 2, 2, and success rate 0. And then let's run that a couple of times. Trial 1, trial I, end of trial I, let me see, so 2, 2, 2, 2, 2, 2, 2, 2, 2, 2, 2, 2. So here it just stayed at the same flower, here it stayed at the same flower. Here it went from 1 to 2, 1, 2 and 0, 1, 2, 0 and 1. 1, 2, 0 and 1. So how come this doesn't count as a success? Oh, because oh, okay, so it doesn't have to be always 3, it has to be larger than 2, not 3. Because we started with 1 and I need to get pollinated by one other one. So this test here is less than 2. If this is less than 2, yes. And then here we have 0, 2, 0, 0, 2, 0, 1. Yeah, that would be one solution. And now that should be correct. However, I need to put in my updated version 0.11. To get rid of all the print statements. So this is correct now. Now we can run more trials. Let's run one for up to 1,000. And then our success rate is 0.144, which is close enough to the rate that we get through analysis, which would be 0.148. And now we can run our experiments. Let's make them a little bit longer. Actually, I just leave them there close enough. And here's our pollination curves. Not so much changed now. the actual values are different, but the behavior of the curves is sort of what you would expect. Here we have some white swings. That's due to the fact that I only run 100 trials. If I run 1,000, then that variance should be much less. But as you can see, it's very easy with Matplotlib to do visualization of the results. In this case, we used it to debug our code to make sure that the simulation actually matches the question that we were trying to answer. And there's many other kinds of drawings, visualizations, analysis that you can do using Matplotlib and NumPy, which is why it is one of the most popular framework for any kind of machine learning at the moment, and other kinds of AI algorithms. Especially using Jupyter notebooks like this is a very common way of dealing with data science applications. And you can see why it is really very nice to work with, and I suggest you learn how to use it as a tool. Will be able to greatly improve your visualization of the results, your exploration of the data that you have available, and your analysis. And that's true for robotics tasks, machine learning tasks, AI tasks, any kind of programming task, really. So let me delete this one. And now we've been going for about 2 hours. I want to take a short break, 15 minutes, and then I'll meet you again at 20:30. Okay. Okay, so we're back again to the second half of our class. Let me just finish the drink. And let's focus our attention again on affine transformations, because that's the fundamental issue in kinematics. So we need to solve rotations and translations first before we can look at the issue of forward and inverse kinematics for our humanoid robots. I will now continue with our homogeneous coordinates website, lecture notes that we started last time, where we were talking about the arrow. We drew the arrow and then started looking at rotation. So now I'll be using this link. So again, there's also the Twitch stream and the Google Colab notebooks, which will then also be posted on GitHub. Let me just finish them off. So here's our arrow figure. We want to be able to move it around in first 2D space and then 3D space. And now, right now we're considering rotations. So I have a point PT which has coordinates x and y, and now I take that point, rotate it by an angle of theta to a new point PT dash that has coordinates x dash and y dash. Now to solve that problem, we need to take the coordinates of the point and convert them into polar coordinates, which are given by the distance to the origin as well as the angle between the vector to the point and the x-axis. So here our point PT has distance r and angle alpha. Based on that, it's easy to see that we can do that conversion. The length of our vector, the distance to the origin, would be the square root of x squared plus y squared for the initial point, and the angle would be arctang of y and x. Again, I just remind you, if you have to do any kind of inverse tangent function using computer, then use the new atan2 function as opposed to atan, which has a whole bunch of problems. So after rotation then, now the distance to the origin will not have changed, right? Because we're only rotating around the origin, so r will remain the same, but now our angle to the x-axis will be alpha plus theta. So that gives us new set of coordinates. In order to solve this now, we need to know the addition theorem for sine and cosine. And actually this is a very nice and lovely proof. You can look them up on Google, but it's again important to understand what those theorems actually mean. And this is really quite a nice proof. So let me just share this with you. And it also allows you a little bit more experience with programming in Matplotlib. So first, I'm going to draw let's take theta 1 is equal to 50 degrees. Theta 2 is equal to 20 degrees. And again, I highly recommend that you are consistent with your variables and don't mix radians and degrees. So whenever I have a variable, I always, for input or definition, I take it from degrees, convert it into radians. When I print it out to the user, I convert it from radians into degrees, but that's the only time that I change out from radians. Everything internally, the storage in the computer, is all based on radians. So let's plot the first thing. A first line. I'm interested in the sum theorem for sines and cosines. So the sum of the angles is theta 1 plus theta 2. And I want to have the vector. I draw the vector unit length, so length of 1, which means the x coordinate is going to be cosine, and this is going to be sine of the sum of the angles. Draw it as a straight line, and let's set the color to red. So here's our angle. Now this is the line for 70 degrees, right? 20 plus 50, make it 30. So now I want to show the constituent parts. And that will be the length of this. this would be sine So now I have two lines. First one is from 0 to 1 for 70 degrees. This is the 50-degree line, the blue one here. This is now what we're trying to find is, this would be theta 1, theta 2. What we're trying to find is cosine and sine of this red line, right? Because that would be the sum of those. So let me plot this as dash dot dash. Dash dash. Yeah. Let's add the angles. Before I forget. From 0 to theta 1. Theta 1 plus theta 2. Width, height, angle, theta 1. That's theta 1 here. make sure that the aspect ratio is equal. And here we have theta 1 now. And here we have theta 2. Start angle for the arc should be not 0 but theta 1 divided by mass of pi multiplied by 180. Here I actually have to flip it around because plus theta 2 because the arc function requires degrees as input, so it's a little bit unusual. Most of the math libraries in computers always require radians. X Windows also uses degrees. I think it uses degrees multiplied by 10, or yeah, I think multiplied by 10. Theta 1, so this should be the sum of the angles here. Sum of the angles. Sum of the angles. Theta 1 plus theta 2. Oops, don't want that there, but okay. I'll make this one theta 2 and it would be yep, that would be different. It should be theta 1 plus theta 2 divided by 2. Theta 1 plus theta 2 divided by 2. Let's do this one also dashed. And then I can plot what we actually want to find. And that would be math, the cosine, theta 1 plus theta 2 . I'm streaming again, okay. 0. 0. Not minus 10, minus 0.1. About that. 1 be the sine. Green. Then let's make this one cyan. Right, so here, this is the cosine that I'm looking for, and here's the sine, and I can plot some helper lines to see why that is the cosine and the sine. So this is the sine line. And here this is the wrong line. That should be 0, 0. Zero mass sine. And then the endpoint cosine theta 1 plus theta 2 and sine. Right, so then here I can change this. This would be xt. This would be yt. And now our helps lines, for the sine it should go from x to xt, and the y should be yt, yt. Color should be green. Line width equal to 1. And let's plot another helper line here for 0, 0, xt, no, 0 to yt. The x corner will be xt, goes from 0 to yt. Color is green, this color is red. Line width 1. And here we have our helper lines now. So the vector that I'm interested in is this cyan vector here. It has a length of 1. So the red part is what I'm looking for, and the green part here. Right? And that angle consists of 2 parts, theta 1 plus theta 2. So the question is, how can I express that as sines and cosines of, as a function of sines and cosines of theta 1 and theta 2 independently? So in order to prove that point, we will now plot 2 more helper lines, and I make the angles not quite so big, so let's make this one 40 and 30. Then our figure looks like that. So now I want to plot a curve from xt, yt to xc1, yc1. That line is also a construction line. Color is cyan. Line width is 1. So here we have a right angle triangle that goes from theta 1 plus theta 2 vector to the vector for theta 1. Then we draw another one. From xc1, xc1, yc1, 0, color equals blue, line width is 1. And now we have this figure here. So let me plot the x-axis. From 0 to math dot cosine theta 1, from 0 to 0, color is blue, line width is 1, 2 maybe, sure. Plot it as a separate line. Oops. Color is blue. xc1, yc1. Right, so now we're almost finished. Like I said before, we're trying to find the red and the green line, the lengths of the red and the green line here. So now, if I look at this blue line, right, then this blue line here would be the cosine of this angle multiplied by the length of this vector here. Now what's the length of this vector? Think about that. And I will add some more helper lines. So I need to plot one from xc1 to xc1, from yc1 to yt. Color is equal to so for the cosines I've used green and red for the sines. Used red and I used blue here. No consistent color scheming. So this would be a cosine, so I'll make it red. And the next one would be yt, xc1, xt to xc1. And this would be the sine this time. Right. So now if we look at that figure, then here's our figure. I could rotate that. Font dictionary with dash instance keyword arcs. Huh. Thought it was easy to rotate the text, maybe not. Transforms. Oh. Nope, didn't rotate. Okay. Okay, never mind then. And this one is wrong. This shouldn't be cosine, this should be sine for the red line. Yeah. So let's look at the sine first, because that's a little bit easier. If I want to find the green line, right, which is the sine of theta 1 plus theta 2, then what I can do is I can take the sine of this part, the blue part here, plus the red one. Right? Those two added together, this one plus this one, is equal to the green line. Pretty easy to see that. So based on that, we can do our first substitution. Now, the important thing to realize is, what's the length of the blue line? Well, this length from here to there is 1. It's a unit vector. Now, that line here is therefore the cosine of theta 2, because this is the line, right angle triangle, so this will be cosine theta 2. This is sine theta 2. So that means that blue line is going to be the sine of theta 1. The length of this, however, is not unit vector, but it's cosine theta 2. So we will get sine of theta 1 multiplied by cosine theta 2. So the sine of theta 1 plus theta 2 is equal to sine of theta 1 multiplied by cos theta 2 plus. Now I need to figure out what the length of this red line is. Now, if this is theta 2, if this is theta, so if this is theta 1, this is 90 degrees, this is 90 minus theta 1, 90. So this three angles have to add up to 180. So this is 90 minus theta 1 plus 90 has to equal, so this is theta 1 here. Right? Theta 1. This is a right angle triangle. The length of this is the sine of theta 2. So this length will be cosine of theta 1, because this is theta 1. This is 90 minus theta 1. This is theta 1. So this is theta 1 multiplied. So it's cos theta 1 multiplied by the sine of theta 2. Cos theta 1 multiplied sine theta 2. So this is a proof of the first identity for sines and cosines. The sine of theta 1 plus theta 2 is the sine of theta 1 multiplied by the cosine of theta 2 plus cosine of theta 1 multiplied by theta 2. And you can see that the green line here can be constructed out of taking this blue line and this red line here. So now, how about this red line, which is the cosine that we're interested in? In order to find that, what I need to do is I need to take this length from the origin to here and subtract this part, right? So from here to there, minus this will give me the red line that I'm interested in. So that means the cosine, let me just copy it so I don't have to type so much. The cosine of theta 1 plus theta 2, as we said before, the length of this is cos theta 2. So the length of this is cos theta 1 multiplied by cos theta 2. So cos theta 1 multiplied by cos theta 2. But that's too big, right? That's all the way to here. I just want it up to the red line here. So I have to subtract this component. Like I said, this one is sine of theta 2. And this part here, this angle is theta 1. So this component is sine theta 1 multiplied by the sine of theta 2. And there we have it. We just proved the, oh, okay, that one. We just proved the addition theorems for sine and cosine. Let me see if I can format that a little bit nicer. And I can make that figure smaller. Oh, I have to put it here, I think. TD. Right, yes. So sine theta 1 plus theta 2 is sine theta 1 multiplied by cos theta 2 plus cos theta 1. Sine 2 cosine theta 1 plus theta 2 is cos theta 1, cos theta 2, and then minus, not plus. Minus sine theta 1 multiplied by sine theta 2. So now we can apply that to our derivation. This is how far we got. So that means I can expand this now. So that will give me cos theta multiplied by cos alpha minus sine theta sine alpha this will be sine theta multiplied by cos alpha plus cos theta multiplied by sine alpha. And the whole thing multiplied by r. So r cos theta multiplied by cos alpha, alpha. And sine theta, sine alpha, cos theta, sine alpha. Right. So now we can simplify that a bit more. I can multiply in the r on both sides. So end up with this, cos theta, cos alpha r, sine theta multiplied by cosine alpha r plus cos theta, sine alpha r, so on and so forth. And lastly, we can simplify that we can now replace the cosine and the sine, cosine alpha, sine alpha, multiplied by r with x and y. Because r multiplied by the cosine of alpha is equal to x, sine alpha multiplied by r is equal to y. So this means this will be sine is y, right? Cosine is x. Sine theta cos alpha r is equal to x. And cos theta sine alpha r is equal to y. So we get the new x coordinate, x dash, is going to be cos theta x minus sine theta y, and the new y dash coordinate is sine theta multiplied by x plus cos theta multiplied by y. Now mathematicians, when they see this, they like to have things nice and tidy. They are, in order to group these two equations because they belong together, they will we represent them as a matrix, and we can convert them into matrix form. So I can write that as I think I need an array. In matrix form using column vectors, x dash, y dash, and the array centered x dash, y dash, and the array, the right bracket is equal to and this is our rotation now in matrix form. So our rotated coordinates x dash and y dash are going to be cosine theta multiplied by x minus sine theta multiplied by y. Y dash is equal to sine theta multiplied by x plus cosine theta multiplied by y. So now I said before that it's important to understand the way that the rotation matrix is derived, because sometimes you may also see it as follows. So if you blindly Google for it, then sometimes you will not get this answer. Sometimes you see it like this. This is not wrong. It is just using a different interpretation. If the points move, then the first version is correct. The second version is correct if the coordinate system rotates, not the points. So it's important to know what is actually moving and what kind of rotation matrix you actually need. Now it's easy to see if the points move by angle theta 1, for example, or this is the wrong graphic. So in here, if the point PT moves to PT dash, so in this case the points are moving counterclockwise, then by angle theta, then the equation that we derive is correct. If the coordinate system rotates, now that's the same thing as the point moving the other direction towards the clockwise. So sometimes you get the different rotation matrix also if the rotation of the points is clockwise or counterclockwise. So you have to pay attention before you blindly apply the formula. And here we have it. Now, let's have a look at the other kind of operation that we can do on coordinates. And so we can rotate things around, but we can also shift things from here to there. That's called translation. In order to model a translation, we can then derive the equation easily enough. This will be x plus tx will be the new x dash, and y dash is equal to y plus ty. But now we have a problem, because even though the equation is straightforward in this case, how can we represent this in matrix form? Because we would like to have a consistent representation. So if I use a matrix form here, then I would like to do the same for rotation. Then I would like to do the same thing for translation as well. But as you can see, that doesn't really work, because my first number or my x coordinate will be multiplied by something, and my y coordinate will be multiplied by something. So the output is going to be a function of x and y. It'll be proportional to x and y. If x is twice as big, then the change is going to be applied will be also twice as large, because here we multiply them together. In the translation, this change here, tx, ty, is completely independent of the actual values of x and y. So if I want to represent this in matrix form, then we have to use what's called homogeneous coordinates. You can sort of see if I want to have that in matrix form, then I could write it like this: 1 times x plus 0 times y plus 1 times tx, which is x plus tx, right? And y dash would be 0 times x plus 1 times y plus 1 times plus ty multiplied by y. But in that case, the matrices are not square, so they mathematicians also don't like non-square matrices. There's also an another reason for doing it, for extending it to a square matrix, which actually has nothing to do with kinematics. So it's related to a computer vision problem of camera calibration and the modeling of perspective distortion. But for now, it is enough to think about this as the only reason why we do this is the desire to have it as a square matrix. So I need 3 numbers here, so I want to have 3 rows, and I can do that by adding a extra row of 0, 0, 0, 1. And then here I have x dash, y dash, and in my third row I'm going to get a 1 then. So now I have a 3 by 3 matrix. X plus tx is going to be x dash. Y plus ty is going to be y dash. 0 times x plus 0 times y plus 1 times 1 is going to be 1. So in the 2D case, I end up with a 3 by 3 matrix. Now to make these consistent, we also extend it to let me add that to a new slide. And then I take the same idea and apply it to rotation matrices, and I end up with what we had before, cos theta negative sine theta and then 0 sine theta cos theta 0 and 0, 0, 1. And here we have our two transformation matrices as homogeneous coordinates. So in the 2D case, we end up with 3 by 3 matrices. The same idea, same reasoning can be applied to three-dimensional. But in this case, we need then 4 by 4 matrices rather than 3D matrices, 3 by 3 matrices, because we now have 3 coordinates x, y, z if we're dealing in the 3D world. So there we have it. Now we can have some fun with our arrow. I now implemented this function in Python, and I just defined one to rotate around Z. In 2D, I have cos theta, negative sine theta, sine, cos, and translate by tx, ty is 10 tx, 01 ty, 001. So we have our arrow somewhere. Let me check what the coordinates were for that arrow. So we define a function to draw the arrow, and but now I want to do something a bit more interesting. Now what happens if I want to rotate the arrow and have it point at something? So here, this function, it draws my arrow, but I cannot apply rotation or translation or anything to it easily, because I would have to change. It directly uses the rectangles here, right? And the triangle and the square. So I would have to change those numbers here and pass that in. So now what we'll do is we will add an extra parameter to our function to draw the arrow, and that parameter is going to be the transformation matrix that we apply for this drawing. So that means I need to write this as A, and the points that I have I need to take those points and multiply them by the transformation matrix. So that means I need to calculate the matrix multiply using the dot product of the transformation matrix and our first part, which is the rectangle. Now the rectangle right now is in row column, in row order. They're row vectors, right? 0, 0 is the first vector, then 1, 0, 1, 2, 0, 2, 0, 0. In order to do the matrix multiplication, I need to have it in column format. So I need to add the transpose by just saying .t for before I calculate the matrix multiplication. Then here, this would be AR, and this would be AR, and a triangle is equal to a dot triangle dot t. And I need to flip those because now it's in column order. So 0 is row, will have the x coordinate, first row will be the y coordinates. And actually, yeah, okay. Let's do it like that. AT 1 0 and the square is a dot square dot t, and that would be as 0 as is a keyword, so ASQ, ASQ, ASQ1, three, 3, and 2, 5. Oh, and the other problem, of course, is that the points that I pass in, I need them to be I need to have a 1, 1 underneath. So in this case, I can take that matrix and put a row for every column vector x, y. I need to change it to x, y, 1. So if it's 2, 5, it needs to be 2, 5, 1. So I can add those. This would be mp dot v stack triangle dot t and np dot ones length of the triangle and this will be mp dot v stack square dot t length of square mp dot ones length of the square invalid syntax AR0. Probably missed a bracket, yes. Another bracket? Oh, really? So now let's have a look at our arrow. Should be drawn correctly still. So here's our arrow, nothing changed so far. But now I can make it a bit more interesting. I can say the rotation is rotate by Z, rotate the arrow by 140 degrees. In radians. Let's take what color? F0 C0 F0 C0 A0. That'd be very bright. Okay, let's look what it looks like. And size 5. And now I pass in my transformation matrix, in this case rotation 1. So this will not, I should draw, rotate Z is not defined. Didn't run this. Now I have two arrows. The first one is our standard arrow, just the points. The second one is the arrow rotated by 140 degrees around the origin point here, right? So now let's say I don't like the arrow there, then I can also do a translation. Two units in X minus 4 units in Y, then draw this arrow with a green component. So now this arrow moved by 2 units in the X direction and minus 4 units in the Y direction. 2 minus 4. Right? Now the important aspect of this is, and one of the reasons why we chose this matrix formulation using homogeneous coordinates, is that now I can continue to apply transformations, because if I start with my original points here on the right hand side and I do a rotation, then I end up with new coordinates. But these new coordinates are going to be in a form that if I want to do another rotation, I can just apply another matrix. However, it's important that matrices for these what's called compound transformations, they must be left multiplied. So if I do rotation first and then translation, then I have to do rotation, translation multiplied on the left, because matrix multiplication is not associative, so A times commutative, it's not commutative. A times B is not the same thing. It's not equal to B times A if you're dealing with matrices. If it's numbers, then that holds. 2 times 3 is the same as 3 times 2. But matrix A multiplied by matrix B is not the same thing as matrix B multiplied by matrix A. So let's do a compound transformation then. Now the important thing is, in my draw arrow function, the only thing I need to do is pass in a matrix. Now if I take a 3 by 3 matrix, multiply it by a 3 by 3 matrix, I end up with another 3 by 3 matrix. So that's okay. So if I do rotation first, then translation, then I end up with this figure. So let's make this one yellowish. If I do translation first and then rotate, then I end up with this graphic. So here are a compound, and you can see the two results are not equivalent in this case. Sorry, I haven't changed this one yet. Rotation, then translation. So if I start at 0, 0 and then I translate the point to there and then rotate, then I would end up with if I do the translation first, I end up with the cyan figure. If I do the rotation first, then I will get that figure, and then shift it to there, I get the yellow figure. So the cyan one is translate first, then rotate. This one here is translate first, then rotate. This is what you get when you rotate first and then translate. And you can see those two arrows are not the same. So now to finish off, we can do some other transformations that come in handy sometimes. Not necessarily when dealing with robotics and kinematics, but certainly when you're dealing with computer graphics, then what do you expect to happen, or what do you think will happen if I use this kind of transformation matrix? So if my matrix looks like this, then what do you think will happen? Well, in that case, I just apply some factor to x, right? Because it's going to be sx multiplied by x with the other factors ignored. This will be y. So this is not a the kind of transformations that we can apply using this matrix form are called affine transformations. So this version would allow us to do scaling. It allows me to zoom in and zoom out on an image. And then there's another one that also has its uses in computer graphics. Which is called a skewing operation. Now this is usually applied in X and Y dimensions. Yeah, I'll just do it as one. Oops, okay, why? Okay, y1. So here I have a skew in the X direction and a skew in the Y direction that I can define for my matrix. And we'll see the effect in a second. Let's draw some more arrows and define our functions here. So here let's do a scaling operation. Zero 0.52. So now the arrow will be thinner because x coordinate is multiplied by 1/2, and it's going to be taller because the y coordinate is multiplied by 2. So we get this one here. and I can do a skew. And that skew, let's make that 1.5 in X and 0. And then let's draw them. So here I draw the scale 1, and here I draw with skew. One. T2. So here are I did the translation. Ah, here's a translation that I didn't want to draw. This is weird. Yes. So let's do this one. Skew 1. Not a translation. So the yellow one is the result of scaling. Like I said, the arrow now is thinner and twice as tall. And this is the skew. So you can see that the size here hasn't actually changed. But as we go up, as our y coordinate increases, it's sort of offset. It's like the arrow is now tilted all of a sudden, based on the coordinates on our current y coordinates. So the whole shape is now not rotated, right? It's just shifted. These lines, they're all still parallel to the x-axis. This line here is parallel to the x-axis, this one here. So it's not doing a rotation, but it's doing a shifting. And of course, any one of those matrices I can use in a combination of those. These are called the compound matrices. So where do we have the notation first? So let me add the text here. So here I want to get point. Array 0, 0, 1. Transpose. No, not transpose. So text should be x1, y1, and this was rotation after translation. Now here the third one I can ignore. So this is rotation after translation. So first translation, then rotation. Here it's first rotation, then rotation. Which is the yellow figure here. The green one was just the translation. The orange one, the skin colored one, is rotation. So this is rotation, which is just rotation 1. Let's move this one down a little bit. So I want to move it up on the arrow. So let's change this to Y to 2. So now we have rotation there. And now I have them almost all labeled. Translation is here. Let's move that one to 2 as well. Actually, maybe I should change all of them to 2. Okay, and this is the original with nothing applied. That's our blue one here. And of course we can form compound transformations also with the scaling and the skewing operation. So I can scale and skew and rotate and translate and just keep moving things along. The only thing that is important to remember is you must multiply it on the left hand side. So now we have our affine transformations, scale, skews. Now we can have some fun. One thing that we can also do is we can keep applying a transformation. So let's draw a little figure. Now when I draw the arrow, so let's see. I want to draw the arrow. AX color is let's pick an interesting color. 34, 97, 15, or maybe C5. Line width 1, 2, and A as my transformation matrix. That will draw an arrow now. But now I want to change the So I want to take A is equal to A dot let's move it up by 3. And 0 in the y direction. No, it's an arrow, so let's go up by 5. And then rotate it by 15 degrees to the right instead of to the left, so minus 15. And then I want to scale it by 0 0.8, 0 0.8, make it bigger in Y. Dot, translate it, rotate it. So let's see what that looks like. Color, line width. And A is equal to A. It's not rotate, but rotate that. And now we can have some pretty cool graphics. So you can see our arrow shooting off here and being rotated. So that is pretty neat and very useful, of course. Helps you, save you from having to write a whole bunch of commands. Let me make this one a little bit bigger. Extends into Y. Alright, so now you can see our arrow shooting off into space. And let's skew it in the Y direction first. A little bit. And then see what figure we get. Ooh. Okay, now it's shooting off too far and it's skewing the skew. The range is now a little bit too big, 500 to 800, so my arrow doesn't actually show up. Skew it by 1.5. Ooh. Okay, now we can do some other figure. 0.1, of course, not very big. Yeah, and that skews our little arrow even more so now. And we get sort of a spiral shape. Okay, good. That's it as far as homogeneous coordinates in 2D are concerned. homogeneous transformations in 3D. Can be represented by 4 by 4 coordinate transformations. The parameters, of course, will change. So scaling, we would have Sx, Sy, and also Sz, because we can scale in the Z direction as well then. Skewing, we could skew in the X, in the Y, and in the Z direction. And rotation, there will be 3 separate rotation matrices. Around the X, Y, and Z coordinate axis, respectively. But other than that, it's analogous to the 2D case. Of course, translation also changes to 3D, 3 parameters. And there we have our homogeneous transformations now in 3D. So that's it for the lecture today. We managed to cover some of the material that we missed yesterday because I had to cancel the class. I really like this proof. There's other proofs for the addition theorems for sine and cosine, but I think this proof is very elegant. Based on geometry alone, it's very easy to derive the laws that govern the sine of theta 1 plus theta 2, the cosine of theta 1 plus theta 2, and we derived the rotation matrix from first principle, from nothing basically. We didn't use any complex theorems in order to prove that. And then now we can do that. We can apply that to all kinds of drawing operations. That's why, for example, if you look at if you've ever programmed in a game engine, a 3D game engine, or a user interface, then very often, they will have 4 by 4 matrices as primitive data structures. Similarly, 3 by 3 for 2D game engines or 2D user interfaces or image processing. In those cases, that's how you can modify your sprite or the information that you want to draw, the set of points that you want to draw. By explicitly stating the transformation matrix. And any matrix, any 3 by 3 matrix, I can use in order to draw my shape, right? Doesn't really have to mean anything, so we can do just for fun. A is equal to M. So the size that I need would be 3 by 3. No. 2 by 3. Two rows, 3 columns, yes. Minus 0.5 multiplied minus 0.5. So now that gives me matrices with multiplied by 2, which range from -1 to 1. Right. And then underneath I need to put 0, 0, 1 to make it a homogeneous transformation matrix. Then we can draw an arrow. So let's see what kind of shapes we get if we just draw them randomly. And not so many, let's just draw 10. Because it won't be a nice consistent change, it'll just jump around randomly. Not callable. Oh, it's random.random. Double random. So here we have T4. So yeah, now you see all kinds of shapes. This is a fairly interesting one. Skewing all those operations now. In effect, this one you can sort of still see what the shape is. But yes, you now have an infinite playground for moving around or manipulating a series of points in 2D. Now, I mentioned before that the 001 is also used for cameras and the perspective distortion. In this case, you're actually dealing with kx, ky, and kz and you divide the coordinates that you get by the output of the last row. But I don't want to go into more detail about that. If you're interested in that, then you should take the computer vision course where we use that in order to model cameras and their projection. So that's it for today. Thanks for staying with me for so long. Want to continue tomorrow morning. Next class at 9 o'clock. But now we can all have a good night's sleep.